In this lecture, we are going to see the Emf equation of transformers. And in this diagram, you can see a full wave of the flux induced inside the transformer, and this is a sinusoidal wave. Phi m represents the maximum value that the induced EMF can reach, and the time taken by the induced EMF to complete one cycle, be t, right? That time is placed in the x-axis, and flux phi is placed in the y-axis, right? So we are going to deal with this in this lecture. So please be informed about the flux phi m and the maximum value. So let N1 be the number of turns in the primary winding, N2 be the number of turns in the secondary winding, phi m the maximum core flux in Webers, right? Phi m is in the diagram, you can see. So underlying the word core, maximum core flux. It is also the product of magnetic flux density and area, and the supply frequency F that you know, it is in the hertz, right? So the flux, it takes only t by fourth of the time. That means it takes only quarter of the time to reach maximum. So the full wave takes t seconds, right? But the flux takes t by fourth of the seconds to reach the maximum, right? So there is just t by fourth of a second time is required by the flux to reach the maximum, right? So there are 4 quarters, so it deals with only t by fourth of the second. So the time taken by the flux phi to reach the maximum phi m is t by 4 second. So therefore the average value, the average induced flux is equal to maximum value of flux divided by the time taken. So the time taken is t by 4. As you all know, time is the inverse of frequency. T is equal to 1 by f. So if you want t by 4, you have to multiply both sides by 1 by 4. So if you do that, t by 4 will be equal to 1 by 4f. So you can substitute the value of t by 4 with 1 by 4f. So phi m divided by 1 by 4f will be giving you, can rearrange this, and it will be giving you 4f phi m. So this is the average induced flux in the transformer, right? So this flux is also the average. So this flux also gives you the value of the induced EMF here. So the flux per phase or flux per turn will give you the induced EMF. So the induced EMF per turn is the same as the average flux. So 4f phi m volt, right? So after finding this, we need to find volts. You have to mention the units. So we need to find the root mean square RMS value of the induced EMF. RMS value of the induced EMF. So that is equal to, that is the product of form factor and average value. So this is a sinusoidally varying waveform. So the form factor of sinusoidal wave is 1.11, right? So 1.11 multiplied by average value 4f phi m. So rearranging this, you will get 4.44 f phi m, right? So this is the root mean square of the induced EMF, right? So our motive is to find the EMF equation of the transformer. The transformer has two windings, primary and the secondary, right? So the EMF induced in the primary winding is equal to root mean square and the product of number of turns, RMS value, and number of turns in the primary. So by our assumption, the number of turns in the primary is N1. So number of turns. So root mean square is nothing but 4.44 F5 into N1, right? So this is nothing but the EMF induced in the primary winding, right? Instead of phi m, we can rewrite that into Bm and A. So that is in your assumptions which we made earlier. So this is nothing but the EMF induced in the primary coil or primary winding when it is volts, right? If you require EMF induced in the secondary winding, you can do this. E2 is equal to 4.44 F Bm area of cross section into N2, number of turns in the secondary, it is volts, right? So if you divide this equation, both equations, E2 and E1, right, if you can try to divide this, so the common terms are 4.44 Fi or BMA, they are common and they get cancelled, right? So the remaining terms are N2 divided by N1, right? So this gives you the transformation ratio, K. So K stands for the voltage transformation ratio, right? So it determines how much voltage is transferred and how efficiently the system is able to transfer, right? So if you have any doubts, please leave us a comment and let us know. Thank you.